Hi, welcome to Code to Scale. This is another video in database internal series where we discuss B-tree lookup complexity as well as the node splits phenomenon that happens during inserts in B-tree. Okay, so without any delay, let's get started. So B-tree lookup complexity can be viewed from two standpoints. One is the number of block transfers and another one is the number of comparisons done during lookup. So let's cover them one by one, and let's start from what calculating the number of block transfers mean, right? In the context of B trees. So now typically what happens is each B tree, it fits into a single disk block, typically 4 KB in size, right? Now at max, the number of disk transfers would be equal to the height of B tree, right? Because let's assume that, the height of B tree is 3. Typically it would, let's assume that the node that you're looking for exists at the bottommost layer of the tree. So that is why I'm saying at max, in the worst case scenario, the number of disk transfers would be equal to the height of B tree. Now the number of disk transfers is equal to the height of B tree because each level requires reading one disk block, right? This is important. Pretty straightforward stuff, nothing complex here. Whatever the number of disk transfers you are referring to, at worst it is going to be the height of B tree. Why? Because each level requires reading one disk block each, and because you're doing binary search, at max you'd be reading one disk block at each level, right? So let's understand this with an example. So let's assume that the total number of keys stored is 1 million, right? And let's assume that the B tree has a branching factor of 100. Now what is a branching factor? It essentially means that each node can have up to 100 children, right? So in this case, the height of B tree is log base km, which is 3, right? So even for 1 million keys, at max, the number of disk transfers that you are doing, because each node, as I said, is stored in a disk block. So the number of disk transfers at max you are doing is 3, right? So one thing that I want to mention, I'm just using this formula for the height of a tree, height of a k array tree. I'm not covering the mathematical aspects of how this formula is derived, but it's a simple geometric progression formula, that's all. You can read about it on any source, pretty straightforward stuff as well, right? So to recap on the B-tree lookup complexity and what it depends on, the first thing that we covered is it depends on the number of block transfers, and at worst it depends on the height of B-tree. And height of B-tree, because each level it requires reading one disk block, right? Cool. Moving on to the next level, which is calculating the number of comparisons done during lookup. So this is pretty straightforward because from the perspective of number of comparison, the logarithm is base 2 because you are using binary search algorithm, right? So since searching a key inside each node is doing binary search, the complexity is pretty straightforward, which is log base 2 m. So I think I've forgot to mention, wherever I'm referring m in this video, that means the number of elements. For example, here I think I have mentioned that the total number of keys stored in the B tree is 1 million. Same thing goes for calculating the number of comparisons during lookup. The complexity is going to be log base to m. So number of comparisons at worst would be log base to m, and the number of disk transfers would be equal to the height of B tree, which is log base k m, and k is the branching factor, right? Cool. Now let's see how the B tree lookup algorithm looks like. Let's say you are searching for a key in a B tree. What actually happens under the hood, right? So these are the steps that the algorithm follows. What happens is you start from the root node, you perform binary search on the key that you're searching for. You compare the search key with the keys stored in the root node until it finds the first separator key. If you are unfamiliar with separator key in the context of B trees, I would recommend you watch one of the older videos in the database internals series on Code to Scale. I think that is a great explainer of what separator keys are and why they are actually required, right? Now, until we find the first separator key that is greater than the searched value. Now, previous step, has located a searched subtree, meaning whatever element you're searching for, it is going to be in the searched subtree. Now, as soon as we find the subtree, we follow the pointer that corresponds to it and repeat the same process until what point? Until we reach the target leaf node. Now, that target leaf node is where we either find the search key, whatever you're looking for, or conclude that, hey, this key is not present in the tree. Now, keep in mind a couple of things here. So B tree does not store data records only in leaf nodes, but for the sake of this conversation and the sake of this video, we will assume that the data is key and the corresponding data is stored only in the leaf nodes. Now, in a standard B tree, data records can be stored in both internal nodes, which are non-leaf nodes, and leaf nodes both. So this distinguishes B tree from other tree structures like B plus tree, where data is stored at leaf nodes. So typically, if you're reading blogs, B plus tree and B trees, they are kind of referred to interchangeably. But I just wanted to kind of clear this as well, that for the sake of this video, we will refer to trees where data is only stored in leaf nodes, right? So usually B trees are better at holding the actual data, and B plus trees are more efficient at indexing aspect, right? Cool. I hope this is clear until now. Now let's jump to more interesting aspects of B tree. So B tree node splits, right? So splits, when do they happen? Splits usually happen when we are inserting a value into the B tree, right? Now to insert a value into B tree, we first have to locate the target leaf, right? Why target leaf? Because we said and we assumed that the data is only going to be stored in the leaf node, and we try to find the insertion point. For this, we use whatever lookup algorithm we just discussed, which is you start from the root node, do binary search, locate the searched subtree, and keep on repeating this until you reach a leaf node where you either find the element or you say that, okay, it is not present, right? Now, once you are using the lookup algorithm, if the target node does not have enough room available, we say that the node has overflowed, right? And it has to be split. So one thing is, these node splits, right, they usually only happen during insertion, right? I hope this makes sense, right? You are trying to insert an element, and what if the existing data structure is already full? So you have to do some operation on the data structure such that the new element can be accommodated, right? Cool. So node is split if the following conditions are met. What is the condition for leaf node? So a leaf node typically can hold up to n key value pairs, and inserting one more key value pair brings it over its max capacity, which is what? N, right? And for non-leaf nodes, if the node can hold up to n plus 1 pointers, inserting one more pointers brings it over its max capacity, which is again n plus 1. So if you notice, for leaf nodes, we are only talking about key value pair, and for non-leaf nodes, we are only talking about pointers. Why? Because we assumed that the leaf nodes are only responsible for storing the data, and the non-leaf nodes only store pointers, right? Cool. Now let's see what is actually happening before and after split, right? So assume that this is your typical B tree with your keys. It accommodates 3 keys and 4 pointers, 1, 2, and 3 keys, and 1, 2, 3, and 4 pointers. Now let's assume that for this particular B tree, you want to insert the element 11. So what you do typically is, since this is your leaf node, right, you split it down the middle and you create a new leaf node, right? And whatever elements are in the second half of this split leaf node, you insert them in a newly created leaf node, and you'll have essentially just this element. Now if you are trying to insert 11, you have vacant spaces which you can insert here. Now what happens to the separator key? You essentially promote this 13 to become a separator key, and this 18 moves to the next space. So assume that all the empty blocks, right, these are vacant, these are not filled, right? So before split, your tree looks like this. And after the split, where you split it down half the way, middle way, and then you created a new leaf node, and you moved elements 13 and 15 to the new leaf node, still one place empty. You moved 13 here, 18 here, and then you will have 11 here, and this essentially will still be vacant, right? So you split, you create a new node, move second half of the node that is being split to the new node, and take this element, which is the first element of the new node, and promote it as a separator key, right? So I think this will get more clear if you look at the after split picture. So what happened is you added 11 here, you created a new node, which is a leaf node, you moved 13 and 15. So earlier 13 and 15 belonged to the previous leaf node. Now they are part of a newly created leaf node, and 11 became a part of the older node. It is essentially split down the middle, as I was saying. Now what happens to the separator key? Whatever the key was when you were splitting it down, 13 was the key, that key will be promoted to a separator key, so that whenever a lookup happens, you can leverage that separator key. So typically if 13 is the separator key, the values stored here will be less than 13, which is being satisfied here, right? So this is the process where leaf node split is happening during insertion of element 11. So I hope this is clear, right? Now splits are done by accommodating allocating a new node. We had allocated a new node, this is the new node. Transferring half the element from the splitting node to it, that also we did. Once we split it down the middle, 13 and 15 were transferred to the new node, that also checks out. And adding its first key and pointer to the parent node. The first key is added to the parent node, and 13's pointer is also added to the parent node. So everything checks out here. So in this way we say that this 13 key is promoted, and whatever we are splitting down, sorry for the noise, I think I'm getting some pagination alerts from one of my services. So 13 is splitting down the middle, and this is called the middle point, right? So I hope this makes sense. Okay, so now in this way we've said that okay, the key is promoted, and we have also identified the split point, right? These are just nomenclatures, you don't need to worry about them. Now you know that whenever you're inserting something in an index, what is actually happening under the hood in the database, right? That is why when you are applying an index, usually if your team is handling a critical service, you would be asked that do you really need this index, because this operation is going to be performed on a large data set and it may take time. So you will plan your release accordingly where it has minimal impact. So this is also like a real world scenario where you can sorry about that as well. So where you can think that okay, if I'm applying an index update on my database, how is it actually going to affect the traffic that my service is serving? Is the database going to be available? Should I create a replica while the index update is happening on the master node or main node of the database? All these things you will have to think, right? Awesome, cool. Now if the parent node is full, what happens, right? Good question. So parent node is full and it does not have any space available for the promoted key and pointer to the newly created node. That parent node has to be split as well, right? And the worst part is this operation can propagate recursively all the way to the root node, right? So this is one caveat which you should also consider if you're designing systems where frequent index updates are applied. This also is one possibility, and this is an expensive operation, right? Awesome, cool. So node splits, what in summary it looks like is: step 1, you allocate a new node. Step 2, you copy half the element from the splitting node to the new one, right? That is what we did. First we allocated the new node, then you split it down in the middle and copy these two elements to this one, which is the new node. Place the new element into the corresponding node, that also we did. The new element was 11, that was placed into this node. And the last step is parent of the split node. In the parent of the split node, add a separator key and a pointer to the new node. So this is the new node. You have added a pointer and a separator key as well, right? So I hope now you are able to understand what is happening under the hood when a database index update is applied to your B tree, and you are, I think, all set in terms of understanding what's happening under the hood. Yeah, thank you so much for this one. I hope this video added value. So I'm also thinking of kind of starting a systems design series, focusing essentially on microservices, distributed systems. So if you have anything in mind, do comment, engage, and I'd be glad if you found value in these videos. Thank you so much. I'll see you in the next one.